at the starry skies with reverence and wonder, laid the foundation for an endless quest to understand what lies beyond our world. We observed the movement of celestial bodies, sought to comprehend their cycles and patterns, built astronomical observatories, and created myths to explain the origin of the universe and our place within it. Each generation contributed to this ceaseless pursuit, passing down accumulated knowledge and a profound sense of awe at the majesty of the cosmos to future generations. Over time, our tools for understanding the universe became more sophisticated. Technological advancements have allowed humanity to peer into the farthest reaches of the cosmos, to witness the light from distant galaxies, and to observe the birth of star systems. We have learned to use telescopes, satellites, and space probes to explore space, revealing many mysteries hidden within the vast expanses. Yet, as we discover more, new questions arise, questions that are even more complex and profound. What is the universe? How did it come into existence? What role does humanity play in it? These questions remain relevant today, despite all the achievements of science and technology. Modern cosmology is a science that not only unveils the mysteries of the universe's origin and evolution, but also helps us understand the nature of time and space, the forces that govern galaxies, stars, and planets. At the core of these studies lie the fundamental laws of physics, which explain how the initial singularity known as the Big Bang gave birth to the universe approximately 13.8 billion years ago. This moment, filled with energy and matter, marked the beginning of everything we know, the beginning of time, space, and all that fills the cosmos. From chaos emerged structure, stars, and galaxies, within which planets eventually formed, one of which became our home. Despite our insignificance on the cosmic scale, humanity has always strived to understand its place in this vast expanse. We are but specks in the infinity, yet within our minds and hearts burns a desire for knowledge. How did life arise on Earth? Are we alone in the universe? What future awaits humanity? These questions present not only scientific but also philosophical challenges, prompting us to contemplate the meaning of existence and humanity's role in the cosmic scale. Throughout history, we have sought answers to these questions, yet each answer we find leads to new mysteries. We see stars that extinguished millions of years ago, observe galaxies that we will never approach, and realize that our lives are but a fleeting moment in the infinite chain of events occurring in the universe. In this text, we will embark on a fascinating journey through the vastness of space, from the origins of the universe to its possible end. We will explore how our understanding of the cosmos has evolved, what discoveries scientists have made, and what questions remain unanswered. We will also seek to understand humanity's place in this infinite universe and how our understanding of space can influence our future. In this journey, we will consider not only scientific aspects, but also the philosophical and cultural implication of our discoveries, striving to comprehend what it means to be human in such a vast and mysterious world. Space is not just the void between stars, it is an ocean of time and matter, where every atom of our bodies was born in the hearts of distant stars. Understanding this connection to the cosmos opens up new horizons, driving us to further exploration, new discoveries, and perhaps a re-evaluation of our place in this grand cosmic order. We embark on this journey not only to seek answers, but also to experience the beauty and grandeur of the universe, to realize our connection to it, and to find inspiration in its boundlessness. The universe we inhabit is a grand and awe-inspiring object of study. It is home to billions of galaxies, each containing billions of stars and an incalculable number of planets, comets, and asteroids. Everything we see and everything that exists is governed by the same physical laws that describe the behavior of matter and energy. But how did this vast and complex structure come into being? The question of the universe's origin remains one of the most profound and intriguing mysteries of modern science. According to the prevailing theory, our universe emerged from a state of extremely high density and temperature around 13.8 billion years ago in an event we refer to as the Big Bang. The Big Bang is not merely an explosion in the conventional sense. Rather, it represents the moment when space and time, as we know them, began to exist. At this moment, all matter and energy were concentrated in a single point, known as a singularity. This state was so extreme that the physical laws we use to describe everyday reality could not be applied. Gravity, electromagnetic forces, strong and weak interactions, all these fundamental forces existed in a form that we have yet to fully comprehend. It was a moment of pure potentiality, a moment when everything that exists today was in a nascent state, waiting to be born. From this singularity, the universe began to expand, and this expansion continues to this day. This process can be imagined as the incredibly rapid inflation of space, where every point moves away from every other point, similar to how points on the surface of an inflating balloon move away from each other. It is crucial to note that this expansion is not happening within pre-existing space. Rather, space itself is expanding. This distinction highlights the uniqueness of the Big Bang as an event that initiated not only matter and energy, but also the very concepts of space and time. Initially, immediately after the Big Bang, the universe was incredibly hot and dense. Temperatures reached trillions of degrees, and matter existed in a form with no modern analog. In these conditions, elementary particles such as quarks and gluons were in a state of free movement, forming a kind of soup. These particles interacted with each other, constantly being created and annihilated until the temperature gradually dropped to the point where quarks could combine to form protons and neutrons, the building blocks of atomic nuclei. Something remarkable was occurring. From the primordial chaos and disorder, ordered, structured matter began to emerge. Within the first few minutes after the Big Bang, processes of nucleosynthesis began, leading to the formation of the first nuclei of light elements, such as hydrogen and helium. These processes occurred under conditions where the density and temperature were so high that individual nuclei could collide and fuse, forming heavier elements. This initial nucleosynthesis concluded relatively quickly, leaving behind a universe primarily filled with hydrogen and helium, along with trace amounts of lithium and other light elements. These light elements became the foundation for the subsequent formation of stars, galaxies, and all the structures we observe today. It is important to note that this process was not random. It followed specific physical laws that operated with incredible precision and predictability, creating the conditions necessary for the formation of complex structures from the primordial material. Thus, the Big Bang not only marked the beginning of everything that exists, but also laid the groundwork for the development of the universe as we know it. One of the key pieces of evidence for the Big Bang theory is the existence of the cosmic microwave background radiation, CMBR. This radiation, a sort of echo of the Big Bang, represents the relic light left over after the universe cooled and became transparent to photons. In the first moments after the Big Bang, the universe was opaque to radiation due to its high density and temperature. Photons, particles of light, constantly collided with electrons and other particles unable to travel freely. However, about 380,000 years after the Big Bang, the temperature dropped to the point where protons and electrons could combine to form neutral hydrogen atoms. This process, known as recombination, made the universe transparent to light. From this moment on, photons were able to move freely, and this radiation, which we observe today as the CMBR, became a sort of photographic imprint of the early universe. The CMBR reveals that the universe was nearly homogeneous in its early stages, with very slight density fluctuations. These fluctuations are believed to have been caused by quantum processes occurring during the moment of inflation, and eventually became the seeds for the formation of galaxies and star systems that we observe today. These small density variations became the regions where gravity began to concentrate matter, leading to the formation of the first stars and galaxies. The discovery of the CMBR in 1965 by Arnaud Penzias and Robert Wilson was a crucial confirmation of the Big Bang model and provided scientists with a deeper understanding of the early stages of the universe's development. Detailed study of the CMBR using modern satellites such as COBE, WMAP, and Planck has allowed us to create an accurate map of the early universe, measuring its age, composition, and density. These data confirm that the universe is indeed expanding, and that its history began with the hot, dense state we call the Big Bang. While the Big Bang theory gives us a general picture of the universe's origin, it does not explain all the details. For example, it cannot account for why the universe appears homogeneous and isotropic, that is the same in every direction, on large scales. Questions related to the flatness, homogeneity, and lack of magnetic monopoles in the universe remained unresolved within the framework of the classical Big Bang theory. To address these issues, the inflationary theory was proposed, which suggests that in the first fractions of a second after the Big Bang, the universe underwent a period of exponential expansion known as inflation. Inflation was a brief but extremely powerful period of expansion during which the size of the universe increased by trillions of times in a minuscule amount of time. This process smoothed out any initial irregularities and made the universe nearly uniform in all directions. Without inflation, different regions of the universe, located far apart from each other, would not have been able to agree on their properties, as the speed of light limits the exchange of information between them. However, inflation explains how these regions could come to such an agreement despite their distance. Inflation resolved several problems of the standard Big Bang model. First, it explained the homogeneity and isotropy of the universe, as during inflation, any initial inhomogeneous distribution of matter and energy was smoothed out. Second, the inflationary theory provided an explanation for the origin of the density fluctuations that led to the formation of structures such as galaxies and galaxy clusters. These fluctuations arose from quantum fluctuations, which were stretched to macroscopic sizes during inflation. Additionally, the inflationary theory predicts the existence of primordial gravitational waves, ripples in space-time that could have been generated by this rapid expansion. The search for traces of these waves in the CMBR is one of the tasks of modern cosmology and could be key to confirming or refuting the inflationary model. Inflation also opens the door to deeper questions about the nature of the very beginning of time and space. What caused inflation? What conditions led to its initiation and termination? How are these processes related to quantum gravity and possible theories of everything? These questions remain subjects of active research, and their resolution could lead to a new understanding of not only the universe's origin, but also the fundamental laws of nature. Thus, the Big Bang and the subsequent inflation laid the foundation for the formation of our universe as we know it. This beginning, filled with both revealed mysteries and new questions, is only the first step on a long journey that scientists continue to explore, striving to understand both the universe itself and our place within it. After the period of inflation ended, the universe continued to expand, but at a much slower pace. This stage can be seen as the beginning of a long process during which the universe began to take on its modern characteristics. Space was still filled with hot and dense gas, composed of elementary particles, which were just beginning to form into more complex structures. It was during this phase that processes began, leading to the emergence of atoms, stars, galaxies, and other cosmic objects that we observe today. Approximately 380,000 years after the Big Bang, the temperature of the universe decreased to the point where protons and electrons could combine to form neutral hydrogen atoms. This process, known as recombination, marked a significant milestone in the history of the universe. Before this moment, free electrons hindered the propagation of light, and the universe was opaque. However, after recombination, photons could travel freely, leading to the emergence of the cosmic microwave background radiation, CMBR, which we observe today. Recombination also led to the formation of the first helium atoms and traces of lithium. These light elements formed the foundation for the subsequent formation of stars and galaxies. It is important to note that at this stage, the universe was primarily a dark place, not in the sense of the absence of light, but in the sense of the absence of visible structures. It is believed that this was the beginning of the so-called Dark Age of the universe, when light had not yet been emitted by the first stars, and space was filled only with rarefied gas and dark matter. Even during this time, important processes were occurring. Dark matter, which does not interact with ordinary matter electromagnetically, but exerts gravitational influence, began to concentrate in dense regions, forming a sort of skeleton for future galaxies. This process of gravitational contraction of matter into dense regions became the foundation for the formation of the first stars and galaxies. Several 100 million years passed after the Big Bang before the first stars began to form. These stars, known as population 3 stars, became the first sources of light in the young universe. They consisted almost entirely of hydrogen and helium, since heavier elements did not yet exist. These stars were much more massive and brighter than modern stars, with masses exceeding hundreds of solar masses, and their lives were short and turbulent. Population 3 stars played a key role in the processes of nucleosynthesis, enriching the interstellar space with heavier elements such as carbon, oxygen, and iron. These elements, known as metals in astrophysics, became the basis for the subsequent formation of planets and more complex chemical compounds necessary for the emergence of life. These early stars also contributed to the ionization of hydrogen in the surrounding space, a process known as the epoch of reionization. Reionization was the process in which the ultraviolet radiation from the first stars and galaxies ionized neutral hydrogen, splitting it into protons and electrons. This process ended the Dark Age and ushered in a new era where visible structures, stars, galaxies, and galaxy clusters began to form. Reionization was an important stage in the evolution of the universe, as it laid the foundation for the formation of the first galaxies and large-scale structures we observe today. As population 3 stars evolved and ended their lives in powerful supernova explosions, they enriched the surrounding space with heavy elements, creating the conditions for the formation of subsequent generations of stars, population 2 and population 1 stars, which make up most of the stars observed today. These subsequent generations of stars became the building blocks for the formation of galaxies, such as our galaxy, the Milky Way. As the universe continued to expand, gravity played a key role in the formation of large-scale structures. Gravitational forces led to the contraction of matter into dense regions, where galaxies, galaxy clusters and superclusters began to form. In these regions, new stars formed, and the interstellar space filled with gas and dust, creating the conditions for the birth of planetary systems. The formation of galaxies and large-scale structures in the cosmos is a complex and multi-stage process involving gravitational interactions, collisions, and mergers of galaxies and the dynamics of dark matter. Dark matter, which makes up most of the mass in the universe, created gravitational wells into which ordinary matter was drawn, forming galaxies and their clusters. Modern astronomy observes various types of galaxies: spiral, elliptical, and irregular. These forms reflect the complex processes of mergers, interactions, and the evolution of galaxies. Spiral galaxies, like our Milky Way, have beautiful spiral arms where stars actively form, from clouds of gas and dust. Elliptical galaxies, on the other hand, are older and more tranquil systems where star formation has nearly ceased. Irregular galaxies have chaotic shapes and are often the result of gravitational interactions or mergers with other galaxies. Galaxy mergers are an important process that significantly impacts their evolution. When two galaxies collide, their stars and gas clouds begin to interact, which can lead to bursts of star formation, the formation of new star clusters, and even changes in the galaxy's shape. In some cases, a merger can lead to the formation of an elliptical galaxy from two spirals. For example, our galaxy, the Milky Way, likely formed from the merger of several smaller galaxies and continues to evolve through the accretion of matter and star systems. In the future, our galaxy will collide with the neighboring Andromeda galaxy, and this collision will lead to the formation of a new, larger galaxy that may become elliptical or lenticular. The development of galaxies and large-scale structures is one of the key processes in the evolution of the universe, and it continues to be studied by astronomers worldwide. Observations made using powerful telescopes like Hubble and James Webb help scientists not only peer into the distant past of the universe, but also understand how it will evolve in the future. These studies give us insight into how the universe gradually evolved from the hot and dense state characteristic of the Big Bang to the grand and complex structure we observe today. The evolution of the universe is a process that continues, and we are part of it. Understanding this process helps us better comprehend our place in this vast and ever-changing cosmic order. The question of whether life is unique to Earth or widespread throughout the universe is one of the most exciting in modern science. Life as we know it requires certain conditions to exist, such as the presence of liquid water, specific temperature ranges, and a particular chemical composition. However, on the scale of the universe, these conditions might be found in the most unexpected places. There are billions of stars, each potentially hosting its planetary system, and while conditions on most of these planets are likely unsuitable for life, even a small percentage of habitable worlds opens vast possibilities for the existence of extraterrestrial life. Earth is the only known place where life exists. The emergence of life on our planet remains one of the greatest mysteries of science. How did life arise from non-living matter? This question has occupied the minds of scientists for centuries. It is believed that life on Earth originated approximately 3.5 to 4 billion years ago, during a period known as the Hadean Era. At that time, Earth was a hot, volcanically active world with an atmosphere rich in carbon dioxide, methane, and ammonia. Despite these extreme conditions, chemical processes occurring in the oceans and atmosphere created the conditions for the emergence of the first organic molecules. The process of life's origin involves several key stages. The first step was chemical evolution, during which simple molecules such as water, methane, ammonia, and carbon dioxide began to form more complex organic compounds, amino acids, nucleotides, and lipids. These molecules could have formed through various natural processes, such as electrical discharges, ultraviolet radiation, or thermal energy, for example, in deep-sea hydrothermal vents. The next critical stage was the aggregation of these organic molecules into more complex structures, proto-organisms capable of self-replication and metabolism. This stage is the most mysterious, as the exact mechanisms that led to the emergence of the first self-replicating systems are still unknown. However, it is believed that RNA molecules, which are capable of both storing genetic information and catalyzing chemical reactions, may have played a crucial role in this process. Over time, these simplest organisms became increasingly complex, passing through stages of evolution that led to the emergence of prokaryotes, then eukaryotes, and eventually multicellular organisms. These changes occurred over billions of years, resulting in the vast diversity of life forms we see today, from microorganisms to complex organisms such as plants, animals, and humans. The origin of life on Earth is also closely tied to the evolution of the environment. For example, the emergence of photosynthesis, which produces oxygen, altered Earth's atmosphere, creating conditions for the development of aerobic organisms and ultimately more complex forms of life. This process also led to the formation of the ozone layer, which protected the planet's surface from harmful ultraviolet radiation. The question of life beyond Earth has been a subject of discussion and speculation for centuries. With the advancement of science, this question has become the focus of serious research. Today, scientists actively study various objects in the solar system and exoplanets located in habitable zones where conditions might be suitable for life. Mars, for instance, has long been considered one of the most likely candidates for harboring life. Recent missions, such as the Curiosity and Perseverance rovers, are exploring the planet's surface for signs of ancient life, such as organic molecules and geological structures indicating the presence of water in the past. Although the surface of Mars today is cold and dry, there is substantial evidence that liquid water may have existed on the planet in the past, a key condition for life. Geological data suggests the existence of rivers, lakes, and possibly entire oceans in ancient times, which could have created favorable conditions for microbial life. Moreover, the moons of the giant planets, such as Europa and Enceladus, also attract the attention of scientists. Beneath their icy crusts, there may be oceans of liquid water, potentially capable of supporting life. The water geysers observed on Enceladus, ejecting plumes into space, indicate the presence of a subsurface ocean that might be heated by hydrothermal vents on the ocean floor. These conditions could be analogous to those that existed on early Earth, representing potential niches for life. However, the search for life is not limited to the solar system. Thanks to advances in astronomy, scientists have discovered thousands of exoplanets, planets orbiting other stars. Some of these exoplanets are located in the so-called habitable zones, where conditions might be suitable for the presence of liquid water. An example of such a planet is Proxima Centauri b, which orbits the star Proxima Centauri, the closest star to us beyond the solar system. The search for life on these exoplanets involves not only observing their atmospheric characteristics, but also searching for biosignatures, chemical traces that could indicate the presence of life. Molecules such as oxygen, methane, and ozone might suggest biological activity if found in significant quantities in the atmospheres of these planets. Current and future telescopes, such as the James Webb Space Telescope, will play a crucial role in searching for these biosignatures and understanding the potential for life beyond Earth. One of the most intriguing questions regarding extraterrestrial life is the so-called Fermi paradox, named after the physicist Enrico Fermi. The question Fermi posed is simple: where is everybody? If life is widespread in the universe, why do we not see any signs of other civilizations? This question has led to numerous theories and speculations about the nature and fate of intelligent life in the universe. There are various answers to this question. One hypothesis suggests that intelligent life in the universe may be extremely rare. Perhaps the conditions necessary for the emergence of intelligent life are so specific that they only occur on a few planets. Moreover, even if intelligent life does emerge, it may not last long due to various threats such as global catastrophes, self-destruction, or technological barriers. Another hypothesis proposes that advanced civilizations might be avoiding contact with us or using technologies that we have not yet detected. This idea is known as the zoo hypothesis, or cosmic quarantine, suggesting that more advanced civilizations might deliberately avoid contact with us, observing us from afar, or even hiding their presence. Perhaps they consider us not yet developed enough for contact or fear interfering with our natural course of evolution. Another theory suggests that we are simply not looking for the right signals or not searching actively enough. Most of our attempts to detect extraterrestrial civilizations are based on radio-astronomical observations, but advanced civilizations might use entirely different means of communication or technologies that we have not yet discovered. The Fermi paradox remains a significant challenge for scientists and philosophers pondering our place in the universe. It raises questions not only about how unique we and our planet are, but also about what it means to be intelligent beings in such a vast and unexplored cosmos. The answers to these questions could change our perception of the universe and our place in it, as well as determine our future actions in the search for extraterrestrial life. Thus, life in the universe remains one of the most mysterious and fascinating topics in modern science. The research continues, and every new step brings us closer to understanding whether we are alone in the universe or part of a larger cosmic community. When we look up at the stars, we confront the immeasurable expanses of the cosmos, which can make us feel insignificant and alone. Space stretches billions of light years in all directions, and within this infinite expanse, Earth seems like nothing more than a tiny grain of sand. Yet, on the other hand, the realization of our place in the universe allows us to understand that we are part of something much greater than ourselves. We are the children of the stars, created from the same material as galaxies, stars, and planets. This awareness brings not only humility, but also inspiration to our existence. One of the most iconic images of our planet is the photograph taken by the Voyager 1 spacecraft from about 6 billion kilometers away from Earth. In this photograph, Earth appears as a tiny, pale blue dot against the vastness of space. This small dot, barely visible in the image, contains everything we know: our history, culture, science, art, and all the lives that have ever existed. This image has become a symbol of our planet and our existence. Reflecting on this photograph, Carl Sagan said, "Everyone you love, everyone you know, everyone you ever heard of, lived out their lives on this tiny mote of dust, suspended in a sunbeam." These words remind us of the fragility and uniqueness of life on Earth. In the grand scale of the universe, our planet is just one among billions of worlds, yet it is our only home. This realization makes us ponder our responsibility toward this planet and toward each other. The pale blue dot effect prompts deep reflections on our role in the universe. It emphasizes how small and fragile our world is, while also underscoring the importance of its preservation. This perspective urges us to care for Earth, to understand that our well-being is inextricably linked to the planet's health. We are the sole guardians of this unique dot in the universe, and its future depends on us. This photograph also symbolizes our unity as a species. Regardless of nationalities, religions, or cultures, we all share this tiny planet. In the vastness of space, our differences seem trivial. We are all on the same cosmic vessel, traveling through the universe, and our destinies are interconnected. This understanding can serve as the foundation for creating a world where respect, cooperation, and care for our common home become the primary values. When considering our place in the universe, we inevitably think about the future of humanity. Will humans ever leave Earth and settle on other planets? This idea, which seemed like science fiction not long ago, is becoming increasingly realistic thanks to advancements in space technology. We are already planning missions to Mars, exploring the potential for resource extraction from asteroids and building international space stations. The colonization of Mars, the construction of space stations, and the exploration of asteroids could all become part of our future. These projects open new horizons and possibilities for expanding humanity's presence beyond Earth. However, we must remember that wherever we go, we carry the responsibility to preserve our cultural and natural heritage. Humanity's future in space depends not only on our technical capabilities, but also on our ethical and philosophical approach to exploring new worlds. We must remember that every step into space should be thoughtful and responsible. Our actions could affect the future of entire planets, and we must act with respect for nature and life if it is discovered on other worlds. The colonization of other planets should not be seen as an opportunity for exploitation or destruction, but as a chance for a new beginning, founded on respect and harmony. Moreover, humanity's space future raises new philosophical and moral questions. How will we interact with possible extraterrestrial life? How will we organize society on other planets? What will laws and rights look like in a spacefaring society? All these questions require deep consideration before we take our first steps beyond our planet. The cosmic perspective also compels us to realize that Earth is our common home, and until we find another habitable place, we must do everything possible to preserve it. Space exploration should not become an excuse for neglecting our duties toward our planet. On the contrary, it should reinforce our understanding of the importance of protecting and preserving Earth as a unique and precious world. Understanding the cosmic perspective is not just a scientific task, but a philosophical reflection on our existence. We live on a small planet in one of billions of star systems in one of billions of galaxies. But it is precisely this realization that helps us see how important every moment of our life is, how unique and valuable our existence is. When we gaze at the stars and grasp the vastness of the cosmos, we are filled with awe at the scale of the universe. This feeling can be both frightening and inspiring. On the one hand, we understand how small and insignificant we are in the grand scheme of the universe. But on the other hand, this awareness makes our lives all the more precious. Every moment, every choice, every action gains meaning in the context of the vast cosmos in which we exist. The cosmos teaches us humility while simultaneously inspiring us to achieve great things. It reminds us that in the face of infinity, every person and every life matters. It also makes us ponder questions that go beyond the ordinary, the nature of time and space, the beginning and end of all that exists, the meaning of existence. These questions drive us to seek answers and strive for knowledge, which in turn defines our place in the vast universe. The cosmic perspective allows us to see the world in its true scale. It shows us that our lives are but brief moments in the history of the universe, yet these moments hold immense significance. This understanding motivates us to explore and learn, to strive for harmony with nature and the universe. Embracing the cosmic perspective can lead us to a new level of spiritual and moral development, to an understanding that we are part of something great and infinite. Ultimately, realizing our place in the universe helps us find meaning in our lives. We are not mere accidental creatures on a tiny planet in a vast galaxy. We are the result of billions of years of evolution, bearers of consciousness, capable of understanding and contemplating the universe. This understanding can inspire us to achieve great things, to create a world where knowledge, respect, and the pursuit of peace and harmony become the core values. Thus, the cosmic perspective is not just a look at the stars, but a deep understanding of our role in this vast cosmic order. It teaches us to see the world more broadly, to think globally, and to act responsibly. This understanding can transform not only our attitude toward space, but also our attitude toward each other and our planet, making us more conscious and wise guardians of life on Earth. Our understanding of the universe is far from complete. Despite all the scientific achievements, there remain questions that challenge our knowledge and imagination. Some of the most enigmatic objects and phenomena studied today are black holes, dark matter, and dark energy. These cosmic phenomena not only astonish and captivate our imagination, but also play a crucial role in the evolution of the universe. They push us to reconsider the fundamental laws of physics and make us wonder what else lies hidden in the vast expanses of space. Black holes are among the strangest and most mysterious objects in the universe. They are regions of space-time with such strong gravity that neither light nor matter can escape their grasp. The term black hole was first coined by American physicist John Wheeler in 1967. Although the concept of these objects dates back to the work of Carl Schwarzschild and Albert Einstein in the early 20th century, black holes form when a massive star exhausts its nuclear fuel and its core collapses under its own gravity. The result is an object with extremely high density and gravity, known as a singularity, surrounded by an event horizon, the boundary beyond which nothing can escape. This zone represents a kind of point of no return, and anything that crosses the event horizon is forever lost to our perception. There are various types of black holes, depending on their mass. The most well-known include stellar mass, black holes ***. These form from the collapse of massive stars and have masses ranging from a few to dozens of solar masses. They can exist alone or in binary systems, where their presence is often detected through interactions with other objects, such as nearby stars or accretion disks. Supermassive black holes. These giants reside in the centers of galaxies and have masses ranging from millions to billions of solar masses. They are believed to play a key role in the evolution of galaxies, significantly influencing their shape, dynamics, and star formation processes. An example of such a supermassive black hole is Sagittarius ** at the center of our galaxy, the Milky Way. ***. Intermediate mass. Black holes ***. These objects, with masses ranging from hundreds to thousands of solar masses, are the subject of active research. Discovering and studying them could provide insights into how supermassive black holes form and evolve over time. One of the most exciting topics in modern astrophysics is the study of the event horizon and what happens inside a black hole. Einstein's theory of relativity predicts that time slows down and space warps around a black hole, leading to paradoxes that require new theories for explanation. The most extreme effects occur near the event horizon, where gravitational forces are so strong that they break down the usual laws of physics. The study of black holes is also closely tied to research on quantum gravity and the nature of space-time. One of the most famous questions in this area is the information paradox associated with black holes. This paradox arises from the fact that black holes, according to Hawking's theory, can evaporate through a process known as Hawking radiation. However, this process challenges the conservation of information in quantum mechanics, representing one of the unresolved problems in modern physics. One of the most intriguing mysteries in cosmology is the nature of dark matter. This invisible substance neither emits nor absorbs light, but its presence can be inferred from its gravitational effects on visible matter, such as stars and galaxies. Dark matter plays a crucial role in forming structures in the universe, such as galaxies and galaxy clusters, and constitutes a significant portion of the universe's total mass. The idea of dark matter was first proposed in 1933 by Swiss astronomer Fritz Zwicky, who noticed that galaxies in the Coma cluster were moving faster than could be explained by the visible matter alone. This effect, known as the missing mass problem, was the first evidence of dark matter's existence. Later, in the 1970s, astronomer Vera Rubin discovered that stars in the outer regions of galaxies were rotating faster than predicted, further indicating the presence of unseen mass. Dark matter makes up about 27% of the universe's mass-energy content, far surpassing the proportion of ordinary baryonic matter, which comprises stars, planets, and us. However, despite its importance, the nature of dark matter remains unknown. Various hypotheses suggest what it might be. One of the most popular hypotheses proposes that dark matter consists of particles that interact weakly with ordinary matter. These particles, if they exist, might be detected through collisions with atoms in specialized detectors located deep underground. Another candidate for dark matter is hypothetical particles, proposed as a solution to the strong interaction problem in quantum chromodynamics. These particles could be detected through their interaction with electromagnetic fields. This hypothesis suggests that dark matter might consist of objects like black holes, neutron stars, or brown dwarfs, which do not emit light but exert gravitational influence. The search for dark matter continues through various experiments, such as particle detectors in underground laboratories and observations of the behavior of galaxies and galaxy clusters. For example, experiments like Lux Zeppelin and Xenon 1T are aimed at detecting WIMPs, while observatories like the Large Hadron Collider also search for signs of these particles in high-energy collisions. However, despite numerous efforts, direct detection of dark matter has not yet occurred, and its nature remains one of the greatest mysteries in modern science. Even more mysterious than dark matter is the phenomenon known as dark energy. This unknown form of energy is responsible for the accelerated expansion of the universe. Dark energy constitutes about 68% of the total mass-energy content of the universe, making it the dominant component of the cosmos. The discovery of the universe's accelerated expansion in 1998, made through observations of Type Ia supernovae, was one of the most important findings in modern cosmology. Scientists were stunned to find that the universe was not only expanding, but doing so at an increasingly faster rate. This discovery led to the introduction of the concept of dark energy. Introduced by Einstein in his equations of general relativity, the cosmological constant describes the energy of the vacuum, which causes the universe's expansion to accelerate. Einstein originally introduced this concept to explain a static universe, but later discarded it, calling it his greatest blunder. However, with the discovery of the universe's accelerated expansion, the idea of the cosmological constant was revived and became a central element of modern cosmology. Another hypothesis suggests the existence of a dynamic field, analogous to the scalar field in physics, that evolves over time and could explain the observed acceleration. This field, known as quintessence, could vary its energy density over time, allowing scientists to explain not only the acceleration, but also its possible changes in the future. Some scientists propose that explaining the accelerated expansion requires revisiting the laws of gravity, such as the theory of relativity. These modifications might include adding new parameters or introducing additional dimensions, which could change our understanding of gravity on large scales. Understanding the nature of dark energy remains one of the biggest unresolved challenges in physics and cosmology. Answers to these questions could lead to a fundamental change in our understanding of the universe and its evolution. For example, if dark energy continues to accelerate the universe's expansion, it could lead to a scenario known as the Big Rip, where galaxies, stars, planets, and even atoms are torn apart by the ever-increasing rate of expansion. Conversely, if dark energy changes its properties over time, it could lead to a slowing or even reversal of the universe's expansion. Study of dark energy is also connected to other fundamental questions, such as the nature of the vacuum and quantum gravity. Discovering and understanding dark energy could provide keys to resolving these problems and lead to the creation of new physics beyond current theories. Thus, black holes, dark matter, and dark energy remain some of the most mysterious and important objects of study in modern science. They force us to rethink how little we know about the universe and drive us to seek new answers and solutions. These cosmic mysteries not only open new horizons of knowledge, but also challenge our understanding of the most fundamental laws of nature. Ultimately, unraveling these mysteries may lead to a new perspective on the universe and our place within it. Cosmology is not only a science, but also a field rich in philosophical reflections, questions about the nature of time and space, the finiteness or infiniteness of the universe, and its possible beginning and end extend beyond traditional science and require contemplation on a deeper level. These questions compel us to think not only about how the universe is structured, but also about the very nature of reality and our place in this grand cosmic order. In this chapter, we delve into the philosophical aspects of time, space, and the anthropic principle, which have continued to intrigue scientists and philosophers for centuries. The question of the nature of time has always captivated the minds of both scientists and philosophers. In everyday life, we perceive time as linear. The past, present, and future follow one another in a strict sequence. This perception of time as something that constantly moves forward is deeply ingrained in our thinking and culture. We measure time with clocks and calendars associated with events and actions, and it has a profound influence on our lives. But is this really how time works? Is time truly linear, or is this just one of its possible manifestations? Modern physics offers various perspectives on the nature of time. In Einstein's theory of relativity, time and space are interconnected in a single space-time continuum, where time can slow down or speed up, depending on the velocity of movement and gravity. This phenomenon, known as time dilation, has been experimentally confirmed in numerous experiments and observations. For example, time on moving spacecraft or near massive objects like black holes flows more slowly compared to time on Earth. This discovery fundamentally altered our understanding of time and its passage, revealing that time is not absolute but depends on the conditions under which it is measured. However, the question remains whether time is linear or if it could be cyclical. Some cosmological models suggest that the universe might undergo cycles of expansion and contraction, leading to recurring big bangs and big crunches. In such a model, time has no beginning or end, but represents an infinite cycle. This idea harks back to ancient philosophical traditions, such as the Hindu concept of yugas, where time is seen as eternal, consisting of endless repeating cycles of birth, death, and rebirth of the universe. Cyclical models of the universe also have modern scientific support. For example, the Big Bounce theory proposes that the universe might experience alternating phases of expansion and contraction. According to this theory, after each big crunch, the universe expands again, which could be interpreted as a new Big Bang. In this model, time could indeed be cyclical, and the current cycle of our universe is just one of an infinite number. Philosophical and religious traditions also offer various views on the nature of time. For instance, in some Eastern philosophies, time is considered an illusion or a phenomenon linked to human perception rather than objective reality. Such concepts challenge the linear perception of time and suggest more complex, multi-dimensional representations of its nature. Understanding the nature of time remains one of the most profound and complex questions in both physics and philosophy. Answers to this question could fundamentally change our understanding of the universe and our place within it. Space, like time, is one of the fundamental components of our perception of the universe. But what exactly is space? Is it infinite, or does it have boundaries? These questions have intrigued scientists and philosophers from ancient times to the present day. We perceive space as something that surrounds us, within which we exist and move. However, when it comes to cosmic scales, our understanding of space becomes far more complex and less certain. According to general relativity, space is curved by the influence of matter and energy. This means that in the presence of massive objects like stars and galaxies, space contracts and stretches. We perceive this curvature as gravity, and it determines how objects move through the cosmos. For example, the orbits of planets around the Sun result from the curvature of space caused by the Sun's gravity. But what does this mean for the nature of space itself? The question remains, is the space of the universe infinite, or is it limited? Modern observations suggest that the universe might be flat on scales exceeding billions of light years. This implies that space might indeed be infinite, continuing in all directions without any boundaries. However, even if space is infinite, this does not rule out the possibility of it being curved and closed. For example, if space has a finite size but no edges, similar to the surface of a sphere, it could mean that by traveling in one direction long enough, we would eventually return to our starting point. Such a model of closed space has been proposed in some cosmological theories, where the universe has a finite volume but no boundaries. The question of the infinity or finiteness of space also has deep philosophical implications. The infinity of space raises questions about the nature of reality, about how we can conceptualize and measure something that has no boundaries. On the other hand, the idea of finite space makes us ponder what might lie beyond its limits, if such limits exist. These questions touch not only on physics, but also on metaphysics, prompting reflections on the nature of existence and what lies beyond our perception. Moreover, the idea of multidimensional space, suggesting the existence of additional dimensions beyond the three we know, is also discussed in the context of string theory and other modern physical theories. These additional dimensions might be curved or compactified at the microscopic level, making them inaccessible to our perception. But they could play a crucial role in fundamental processes occurring in the cosmos. Thus, the question of the nature of space remains one of the most complex and mysterious topics in modern science and philosophy. Answers to this question could not only change our understanding of the universe, but also open new horizons for research and reflection. One of the most remarkable facts about the universe is that it seems fine-tuned for the existence of life. This observation led to the formulation of the anthropic principle, which asserts that the physical laws and constants of the universe are such that they allow for the existence of intelligent beings capable of observing this universe. This principle has sparked numerous scientific and philosophical debates and raises questions about the nature of reality and our place in it. This principle states that we observe the universe as it is, because only in such a universe could we exist. In other words, the physical laws and constants of the universe determine the possibility of intelligent observers, and this is not a coincidence, but an inevitable consequence of our existence. A more radical version asserts that the universe must be such that intelligent observers can exist within it. This version suggests that the existence of life and intelligence is not merely a coincidence, but a fundamental purpose or property of the universe. The anthropic principle raises important philosophical questions. It challenges the idea that our universe is just one of many possible universes and suggests that it should be considered special or even unique. At the same time, it opens the possibility that there are countless other universes with different physical laws where life cannot exist. This leads to the idea of the multiverse, the concept that there are countless universes, each with its unique properties. Some scientists consider the anthropic principle trivial, as it simply states the fact of our existence. From their perspective, we observe the universe as it is, because otherwise we wouldn't be here. However, others see in this principle a profound explanation for why the universe has certain properties, such as the value of the cosmological constant or the relationship between fundamental forces. The anthropic principle also raises philosophical questions about the nature of reality and why our universe has the specific physical laws it does. If there are other universes with different physical laws, what makes our universe so special? This leads to reflections on whether there is a higher purpose or design behind the structure and evolution of the universe. Moreover, the anthropic principle can be linked to the concept of the fine-tuning of the universe. This idea suggests that many physical constants and laws are tuned in such a way as to allow for the existence of life. For example, if the strength of gravity or the electromagnetic interaction were slightly stronger or weaker, stars, planets, and life as we know it would not exist. This prompts us to consider whether this fine-tuning is the result of chance, necessity, or some intentional process. The anthropic principle also challenges our understanding of reality and the scientific method. If we live in one of countless universes where the laws of physics happen to align in such a way as to allow for the existence of life, it could cast doubt on our ability to understand and explain the reasons for these laws. Some philosophers argue that the anthropic principle may require us to reconsider our approach to scientific inquiry and our understanding of the universe. Thus, the anthropic principle presents an important philosophical challenge that forces us to rethink our place in the universe and the nature of reality itself. It opens new horizons for contemplating why the universe is the way it is and what our role is in this vast cosmic order. Ultimately, the anthropic principle may lead us to a new understanding of existence and the nature of the universe, as well as a deeper awareness of our role within it. The question of the universe's future is one of the most fascinating and simultaneously terrifying inquiries. What awaits us and the universe in the distant future? Will it exist forever, or is it destined to end? These questions intrigue not only scientists, but also anyone who contemplates our place in the universe and what ultimately lies ahead. Modern cosmology presents several scenarios for the possible future of the universe, each based on our current understanding of physical laws and observations. There are several scenarios for the possible end of the universe, each grounded in contemporary cosmological models and our understanding of the behavior of matter, energy, and space-time. These scenarios describe potential paths by which the cosmos may evolve or conclude its existence, raising profound philosophical and scientific questions. The Big Rip scenario suggests that the accelerated expansion of the universe, driven by dark energy, will eventually lead to the tearing apart of all structures in the cosmos. In this scenario, dark energy becomes an increasingly dominant force, gradually overcoming the gravitational and other forces binding galaxies, stars, and planets. First, galaxies will be torn apart, followed by the disintegration of stars and planets, and eventually, even atoms and subatomic particles will be ripped apart. This scenario predicts that the universe will end in a state of infinite expansion and destruction, where no complex structures or matter remain, leaving behind an endlessly stretched void. In contrast, the Big Crunch scenario envisions the universe's expansion slowing down and eventually reversing into a contraction. This scenario posits that at some point, gravitational forces will overcome the effects of dark energy, causing the universe to begin collapsing in on itself. All galaxies, stars, and planets will draw closer together, ultimately leading to the concentration of all matter and energy into a single point, a singularity. This process could result in a new Big Bang, initiating the birth of a new universe. Some models suggest that the universe might undergo such cycles repeatedly, with expansion and contraction alternating in a continuous cycle of rebirth. The heat death scenario, also known as the thermal death of the universe, suggests that the universe will continue expanding without any major catastrophes. In this scenario, dark energy will keep accelerating the universe's expansion, but not to the point of tearing apart galaxies and stars. However, eventually, all available energy will be evenly distributed, and the universe will reach a state of maximum entropy. All stars will burn out, cease shining, and star formation will come to an end. The universe will become a cold and dark cosmos, with no available energy left to do work. In this dead cosmos, only weak radiation and scattered elementary particles will exist, drifting through infinite space. This scenario is a variant of heat death, where the universe continues to expand until its temperature approaches absolute zero. Galaxies gradually move away from each other, stars burn out, and space becomes a cold and empty void, where processes that support life and complex structures can no longer occur. This slow fading and freezing of the universe leads to its final death, when there is no energy left for change or motion. The Big Bounce scenario proposes that the universe may undergo cyclical phases of expansion and contraction. After a phase of contraction, when the universe reaches maximum density, a new Big Bang occurs, initiating a new cycle of expansion. This model suggests an infinite alternation of birth and death phases for the universe, with each new universe potentially having its own unique physical laws and parameters. This scenario also raises questions about the nature of time and space, viewing them as cyclical rather than linear phenomena. These scenarios of the universe's end open up not only scientific but also philosophical reflections on the nature of time, space, and existence. Regardless of which scenario proves correct, each serves as a reminder of the fragility and impermanence of the cosmic order in which we exist. Alongside contemplating the fate of the universe, we must also consider humanity's future. What role will we play in cosmic evolution, and what future awaits us in this vast universe? If one day our planet becomes uninhabitable, or if some cosmic catastrophe threatens its existence, will we be able to colonize other planets and star systems? These questions already occupy the minds of scientists, philosophers, and explorers, and the answers may determine the fate of our species. At present, interstellar travel seems far from reality, but research and development in space technology continue. Missions to Mars, the construction of space stations, and the development of new propulsion systems could lay the foundation for humanity's future as a spacefaring civilization. Programs like Elon Musk's Mars Architecture project, which envisions the colonization of the Red Planet, or NASA's plans to return to the Moon and establish a lunar base, are the first steps toward exploring the solar system. However, interstellar travel presents an even greater challenge. Crossing the vast distances between stars requires technologies that we do not yet possess. Nevertheless, scientific research continues, and concepts such as star sails, the use of antimatter, or the warping of space-time, the warp drive principle, may one day make interstellar travel a reality. Space expansion also requires consideration of ethical and philosophical questions. How will we interact with possible extraterrestrial life? If we discover microorganisms or intelligent beings on other planets, what will our moral and ethical obligations to them be? Should we colonize other worlds or leave them untouched, respecting a cosmic right to inviolability? These questions necessitate the development of new approaches to international law and space policy. How will society be organized on other planets? Will we be able to transplant our earthly social structures into space, or will they need to change in response to new conditions? A spacefaring society may face unique challenges, such as the need for self-sufficiency, coping with radiation, microgravity, and long-term isolation. At the same time, space offers new opportunities for social and technological progress, which could transform the very concept of society and the state. Should we strive for the stars, or should we focus on solving problems on Earth? Some philosophers and ecologists argue that before expanding into space, humanity must learn to resolve its issues on its home planet. Environmental crises, social inequality, and political conflicts demand urgent attention and solutions. However, others believe that space exploration could provide a new impetus for human development, inspiring innovation and creating new resources and opportunities for survival and prosperity. Humanity's future in space is also tied to questions of the meaning and purpose of our existence. Is our destiny to explore and colonize space, or should we find meaning in preserving and developing our own planet? These questions require deep reflection and decisions that will determine not only our fate, but the future of all living things. In conclusion, reflections on the cosmic future and the fate of the universe lead us to realize that our lives and actions have significance not only for ourselves, but for the entire cosmos. Whatever the future holds, it is essential to remember that our existence is part of a grand cosmic process, and we bear the responsibility to use our knowledge and resources wisely and responsibly. When we speak about our place in the universe, we cannot avoid the question of the legacy we will leave behind. Humanity has always sought to leave its mark on history, whether through art, science, or great achievements. But what mark will we leave on a cosmic scale? How will our cultural and scientific legacy be preserved and passed on when we are no longer here? These questions provoke deep reflection on how our actions today can influence the distant future and the legacy we will leave for future generations and possibly other intelligent beings in the universe. One of the most famous symbols of humanity's legacy in space is the golden records sent aboard the Voyager 1 and Voyager 2 spacecraft in 1977. These spacecraft were designed to explore the outer planets of the solar system, but their mission includes something far more symbolic. The golden records were conceived as messages that might be discovered and understood by extraterrestrial civilizations billions of years from now. These records contain sounds and images from Earth, including greetings in 55 languages, musical compositions from various cultures, and images of our planet and its inhabitants. Among the sound recordings are sounds of nature, laughter, whale songs, and excerpts from works by Bach, Mozart, Stravinsky, and other composers. Every detail was carefully thought out to convey the essence and beauty of life on Earth. These records serve as a kind of time capsule, carrying information about who we are and how we see the world. The idea of these records reflects a profound desire for humanity to connect with something greater than itself. They symbolize our longing to be understood, our hope that somewhere out there, beyond the solar system, there exist intelligent beings who can comprehend and appreciate our culture and achievements. Even if these messages are never discovered, they remain a symbol of our human nature, the drive to explore, to connect with others, and to seek meaning in the vast expanses of space. The golden records also raise important questions about the nature and significance of our legacy. What do we choose to pass on to future generations or extraterrestrial civilizations? What will be considered important and valuable billions of years from now? These questions compel us to think about how we define and value our cultural and scientific heritage and how our decisions today may impact the future. In addition to material objects like the golden records, humanity has also sent radio signals into space in hopes of contacting other civilizations. One of the most famous such signals was sent in 1974 from the Arecibo Observatory. This Arecibo message contained encoded information about the human race, our solar system, and key chemical elements. The signal, a powerful radio burst, was aimed at the star cluster M13, located about 25,000 light-years from Earth. While the likelihood that the signal will reach its intended recipient is extremely small, this act reflects our desire to establish contact with other intelligent beings. We seek not only knowledge and understanding, but also a connection with others who share our ability to comprehend the universe and strive for knowledge. This desire for contact reflects our nature as social beings who crave communication, even if that contact might be with beings about whom we know nothing. However, these actions are not without philosophical questions. Should we attempt to contact potentially more advanced civilizations? What consequences might this have? Some scientists, like Stephen Hawking, warned that actively sending signals into space could be dangerous, as we do not know the intentions of those who might receive them. These warnings are based on historical experiences where encounters between civilizations with different levels of development on Earth often led to destructive consequences for the less advanced societies. Nevertheless, despite these concerns, many scientists continue to support the search for extraterrestrial intelligence programs, believing that the potential reward, establishing contact with another intelligent life form, justifies the risk. These programs include both active signal sending and passive listening to space for artificial radio waves. If we ever establish contact, it could become the most significant event in human history, capable of transforming our understanding of the universe and our place in it. The question of colonizing other planets is one of the most discussed topics regarding humanity's future. If Earth becomes uninhabitable due to climate change, resource depletion, or other global catastrophes, could we find a new home among the stars? The most likely candidate for the first human colony is Mars, a planet that has long attracted the attention of scientists and explorers due to its relatively favorable conditions. But colonizing Mars is not just a technical challenge. It raises questions about what it means to be human in a completely alien environment. How will our society change when people start living on another planet? How will our social, political, and economic structures adapt to conditions where resources are limited and survival depends on collective effort? These questions require not only scientific, but also philosophical reflection. Colonizing other worlds also raises questions about our approach to new territories. Can we learn from history and avoid the mistakes of the past, when colonization on Earth often led to the destruction of ecosystems and cultures? How will we interact with possible extraterrestrial life if it is discovered? Is there an ethical obligation to preserve and protect other worlds from interference? Space colonization could become one of humanity's greatest adventures, but it also demands a responsible approach. We must understand that expansion into space is not just the continuation of exploring new territories, but also an opportunity to rethink our values and priorities. Instead of repeating the mistakes of the past, we have the chance to create a new, just, and sustainable society based on respect for nature and life. Moreover, there is the question of what cultural and spiritual legacy future space colonists will carry. How will their perception of the world and their place in it change when they live on other planets or in space stations millions of kilometers from Earth? These people will have to adapt to a new reality where familiar earthly landmarks and symbols may lose their significance. They may need to create new forms of culture and religion that reflect their unique experience of life in space. In the context of reflecting on our cosmic legacy, we cannot ignore our home, planet Earth. Despite all our dreams of the stars, our planet remains the only known place in the universe where life can exist as it does now. And this life is extraordinarily fragile. Earth, as numerous studies and observations have shown, is a unique oasis of life. In the vastness of space, surrounded by void and hostile conditions, space reminds us of Earth's fragility and uniqueness. In the vastness of space, Earth is a tiny oasis of life, surrounded by a hostile void. This view from space, especially iconic images of Earth like the pale blue dot, reveals how vulnerable our world is. We realize that our planet is a thin layer of the biosphere supporting all living things, and this layer can be destroyed by our actions. This realization should inspire us to take greater care of our planet and each other. Preserving Earth is not just an ecological task, but a moral obligation. Our cosmic legacy will be defined by how we treat this home and one another. Will we be able to preserve and pass on a planet capable of sustaining life to future generations? Or will we leave behind a devastated ecosystem and depleted resources? Space also teaches us humility and responsibility. Realizing that Earth is our only home in the vastness of space should inspire us to adopt a more responsible approach to our impact on the environment and our role on a cosmic scale. Ultimately, our cosmic legacy will be defined not so much by what we leave behind in space, but by how we care for our common home, planet Earth. When we contemplate the future, we must not only consider the coming decades or centuries, but also look forward to millennia. On this scale, possibilities that seem fantastical today may become reality. The cosmic age we are just beginning to grasp represents not merely a new chapter in human history, but an era that could fundamentally alter our understanding of ourselves and our place in the universe. This future will require not only technological achievements, but also deep philosophical and cultural reflection on our path in space. The idea of interstellar travel has long been the subject of science fiction, but today, scientists seriously consider the possibility of creating interstellar ships. The challenges associated with such journeys are immense. The distances between stars are measured in light years, necessitating the development of technologies capable of achieving incredible speeds or sustaining life over multiple generations. However, projects like Breakthrough Starshot, aimed at developing technologies to send miniature probes to the nearest stars, offer hope that interstellar travel could become a reality in the foreseeable future. Breakthrough Starshot is one of the most ambitious initiatives in this field. The project plans to use ultralight nanosatellites equipped with light sails that will be propelled by powerful laser beams from Earth. This approach allows for achieving a significant fraction of the speed of light, enabling the probes to reach Proxima Centauri in just a few decades. Although the technical and financial challenges remain enormous, the successful implementation of such a project would open new horizons for our species, creating a fully functional interstellar ship capable of carrying a crew and sustaining life during long journeys requires the development of entirely new technologies. We may face the need to solve fundamental issues such as ensuring long-term autonomy, protecting against cosmic radiation, and creating closed ecosystems capable of supporting life for centuries. We might need to develop generation ships, where multiple generations of people will be born and live before reaching their destination. If humanity ever succeeds in creating ships capable of traversing interstellar distances, it will open new horizons for our species. We will be able to begin exploring other star systems, searching for new worlds to colonize, and possibly establishing contact with other intelligent civilizations. However, these achievements will require not only technological progress, but also global cooperation, international efforts, and vast resources to turn these dreams into reality. In the long term, humanity may strive to explore and colonize deep space. This includes not only the colonization of other planets in our solar system, such as Mars and the moons of Jupiter and Saturn, but also the exploration and settlement of other star systems. Such projects will require enormous resources and scientific breakthroughs, but they could become a reality in the distant future. The exploration of deep space will require humanity to adapt to new, unknown conditions. This may mean not only technical preparation, but also evolutionary changes. We may need to adapt our bodies to conditions of microgravity or extreme climate conditions on other planets. Additionally, the exploration of deep space will necessitate the development of new forms of social organization that can maintain social and cultural stability in conditions of long-term isolation and autonomy. The exploration and settlement of other star systems may also require changes in our worldview. How will our self-identification change when we live in societies existing on different planets and in different star systems? How will we interact and exchange knowledge and cultural achievements across vast distances? This may lead to the emergence of new forms of interstellar diplomacy and international space law. The exploration of deep space also raises questions about our moral and ethical obligations. If we discover life on other planets, how will we interact with it? Will we be able to preserve and protect new worlds from our interference, or will we seek to alter them? These questions require deep philosophical reflection and the development of new approaches to our role in space. One of the key aspects of humanity's future in space may be the use of biotechnology and artificial intelligence to expand our capabilities. Space represents an extremely hostile environment for humans. Radiation, extreme temperatures, the absence of atmosphere and gravity make prolonged stays in space dangerous to health. Biotechnology could offer solutions to these problems, such as genetic modification to adapt our bodies to space conditions, or the use of synthetic biology to create sustainable ecosystems on other planets. Moreover, artificial intelligence, AI, could play a crucial role in managing complex space missions, especially in situations where humans cannot participate directly due to hazardous conditions or the duration of journeys. AI could be used for the autonomous operation of spacecraft, the exploration of new planets, and the support of colonies, ensuring their safety and functioning. However, as with any new technology, the use of AI raises important ethical questions. How will we control and manage these technologies? What will happen if AI goes beyond our control? These technologies also raise important questions about what it means to be human. How will our consciousness and society change if we can modify ourselves and create artificial beings? How will we define the boundaries between natural and artificial, between human and machine? In the future, the concept of humanity may expand to include not only biological beings, but also synthetic life forms that coexist with us or even within us. The transformation of humanity also touches on cultural and social aspects. How will we preserve our culture and traditions if we begin to alter ourselves? Will we be able to maintain our values and identity, or will we need to reconsider them in light of new possibilities and challenges? These questions will play a key role in defining our future as a species and as a spacefaring civilization. Alongside scientific and technological progress, our cultural and spiritual development must also keep pace with expanding horizons. The cosmic age will require new philosophical and spiritual paradigms that help us understand our place in the universe and our connection to the cosmos. As we begin to leave Earth and venture into space, it is important to recognize that this journey is not only physical, but also spiritual. The cosmic age poses new questions about the meaning of life and what it means to be human on a cosmic scale. How will we perceive ourselves and our goals when we realize that we are just one of many possible forms of life in the vast universe? What cultural and spiritual values will be important in a world where interstellar travel becomes a reality? We may need to rethink our concepts of the divine, the meaning of existence, and our role in the cosmos. The cosmic age may also lead to the emergence of new forms of religion and spirituality. How will religious concepts be perceived in the context of space life? Will we be able to maintain our spiritual traditions, or will they be transformed under the influence of new knowledge and experiences? We may see the emergence of cosmic religions that reflect our new understanding of the cosmos and our place in it. Culture and art will also play a significant role in the cosmic age. How will we express our feelings and thoughts in a world where our perception of the universe expands beyond Earth? What new forms of art and literature will arise under the influence of the space experience? The cosmos may inspire us to create new artistic and literary genres that reflect our journey through the universe and our attempts to comprehend it. Additionally, the cosmic age will require new approaches to education and upbringing. How will we prepare new generations for life in space? What knowledge and skills will be important in a world where interstellar travel becomes a reality? We may need to create new educational systems that take into account the needs and challenges of space life. The cosmic age opens not only new opportunities, but also new challenges for humanity. It requires not only technical preparation, but also profound cultural, spiritual, and philosophical reflection on our path. We will need to rethink our values and goals to create a society capable of thriving in space while preserving its cultural and spiritual heritage. A look into the future is not just about predicting technologies and scientific achievements. It is also about understanding how our cultural and spiritual development will shape our future in space. We stand on the threshold of a new era, and it is up to us to determine what that future will be. Will it be based on respect, wisdom, and cooperation, or will we repeat the mistakes of the past, taking them to a new level? The answers to these questions will define not only the future of humanity, but also our cosmic legacy. One of the most thrilling aspects of modern cosmological theories is the idea of the multiverse, a concept suggesting the existence of multiple parallel universes, each with its own set of physical laws and parameters. If this theory is true, then our universe is just one among countless others, and its unique characteristics may be merely a coincidence amid infinite variations. This hypothesis not only